Hi everyone, my name is Edi Walger, an educator about color grading, DIT, VFX, and other post-production disciplines like coordination and supervision. This exhibition has content of a course about color theory that I dictate online in Spanish. During the 19th century, there was a controversy between two divergent theories of how the human visual system works. Helmholtz was based on Young's idea that there should be three stimuli associated with color vision, which is verifiable when studying color blindness cases. On the other hand, Herring explains color from an opponent theory, where the green color can be yellowish or blue, but never reddish, and yellow cannot be blue. So all colors can be described as yellow-blue and red-green opponents, and the similarity of any color with these four unique hues, and white and black. A century later, Schrödinger was able to make a relationship between the theories of the 3 and 4 colors, understanding the perception in stages, which was physiologically proven with modern science when studying the role of cone cells and retina ganglions. The interaction of the cones sensitive to the long and medium wavelengths are combined in the next stage as a balance between red and green, and added provide the sensation of brightness, and their results are combined with the cones sensitive to short wavelengths, generating the yellow-blue opposition. Color theories often rely on a graph that projects the color organized in space through different geometries, and we will visit those what we can also find in Baselight. The cubic plot proposed by Benson with its cuboid, built from red, green and blue additive primary, has dimensions that are born from the same origin, which projects a cube supported by a vertex that represents black, 3 lower vertices that represent RGB, 3 superior vertices for secondary colors, and a superior vertex that represents white. Hunter, based on opponent theory, also used the cube, but using one of its sides as a base, which represents black, and develops the lightness attribute in a vertical central axis. The other two axes of the cube are values that are distanced by the central axis in a positive and negative way, orthogonally to each other, called chromatic coordinates A and B. Although both theories result in the same geometric solid, their dimensions express different attributes, since one classifies color from similarity with certain real primaries, and another with the amount of perceptual attributes such as lightness, chromaticity, and similarity with 4 unique hues. Munsell created his own color order system, paying special attention to the scales that are developed within the attributes that create dimensions in their solid, with the aim of respecting in all its axes a perceptual equidistance. Its model results in an irregular form, and not in a platonic solid, since it is not a sphere, cube, cone or cylinder, resulting in a form of a tree. Munsell's color atlas is a collection of pages with color patches designed to result in identical perceptual difference between their hue, chroma and value axes, which is an excellent reference for colorimetric systems and their mathematical modeling of perceptually uniform dimensions. When organizing Munsell patches in the Hunter system, the efficacy of the model and projection can be evaluated and must result in regular intervals. The CIE elaborates in '76 its own model based on coordinates of lightness and chromaticity components, modifying the units with their scales to achieve projecting to the colorimetries of Munsell patches in more equidistant positions with the aim of achieving a perceptually uniform color space. This uniformity is the goal of the CIE LAB space, and also for the chromatic diagram of 1976, based in new dimensions U and V. Pope proposed a cylindrical projection where each axis represents in height the brightness of the color, and the distance with the center the relative saturation of each hue, expressed as an angle. Although the distance with the neutral center is the same for all pure colors, which is not perceptually uniform, the cylindrical plot is very useful for reasoning about color. The problem is to understand what neutral axis is, and it depends on adaptation. Von Gries theorized about how the adaptation to the intensity of the light happens independently for each of the three types of cones, sensitive to long, medium, and short wavelengths, that combined make possible the color vision. Therefore, in the first perceptual stage, before the opponent process, a balance is generated between the maximum bioelectric signals that the LMS cones generate. The most intense stimulus of a scene in general comes from a white object, which faithfully reflects the wavelengths of the scene's light source, causing chromatic adaptation and allowing the object to be recognized as neutral in terms of chromaticity without apparent hue or any saturation. In a digital camera, this adaptation must be made by the photographer from balance tools. In the example image, it is recognized that the garment is a blue sheen, although this object is reflecting any wavelength and not just the shorter wavelength. But since the background of the image is brilliant, the visual system adapts to the orange color that it reflects, which must belong to the color of the light source and not to the local color of the background. Also, colorimetrically, the blue sheen reflects gray light. The visual system recognizes it as blue, colorimetry that would have resulted under a full spectrum light source like the sun. This balance can also be made after the capture of the image, through balance tools in a color correction application, by neutralizing the light source by adding the complementary color. Now, it is possible to work in a next stage with tools that express the color from an opponent process, which is not an absolute colorimetric system, but related to a first stage where the balance must be defined to emulate the adaptation. For example, using base-grade RGB balance parameters. Color operators that express contours from 4 colors are emulating the second perceptual stage based in opponent theory, available in chromogen parameters. In perceptual space, opposition parameters allow to control saturation by altering the proximity of the colors of the image with the neutral axis, proportionally and optionally anamorphic, allowing it to operate differently in each opponent axis, with green or yellow-blue. Simultaneously, it allows interference between opponent signals, allowing mixing red or green channels to the yellow-blue opponent process, or vice versa. To understand the advantages of certain Baselight tools, it is important to understand the concept of monotonic function. These functions do not invert the direction ever. If they are growing, they never reduce, and if they are decreasing, they never increase. Tools that allow no monotonic functions, for example in certain brightness control, can generate undesirable effects such as solarization, as shown by the example image, or also bending. Once the achromatic axis is defined, this can be altered with a non-monotonic function based on a spline, which has control points that define tangents and tension. This allows the growing bright control curve to define a decreasing part, which can invert the tonal curve in a middle part. On the other hand, a parameter-based tool with pivots in mid-gray and diffuse white allows true monotonic contrast control that works naturally and are unable to damage the image. The same goes for hue controls. The qualifiers that mask a range of hues allow one to carry a portion of the chromatic circle above another, thus producing a non-monotonic edition. That is why the fixed control of the 6 notorious hues allow minor turns to a sixth of the circumference to avoid non-monotonic functions. But these fixed angles are not very versatile. In Chromotion, there are tools allowed to alter chromatic circle sectors, such as the squash sector, that allow you to bring many hue angles to a selected value, by compressing hues with cosmetic effects in the image, or with the skew sector caused an inclination towards one of the quadrants of the opponent process. This tool also enables the opponent process to be rotated, so that the user can define which colors are phased in their chromatic axis. The spectral colors that arise from the prism from a linear mixture between the violet and red, and these colors produce of visible monochromatic wavelengths in the dispersion of the light, are usually represented at the outer contour of the chromatic diagrams. These colorful and purity colors were organized by Newton in a wheel to oppose pairs which result in a white at mixing. Maxwell had built an optical mixing device painting with 3 pigments a paper disc that, when turning very fast, seemed to result in new colors. As these colors were subtractive, they did not get the color of Newton's prismatic colors, and that is why it represents Newton's circle outside a triangle, which represents the limited chromatic reproduction capacity of its device. On the other hand, Helmholtz tried to improve the place of the spectrum, the spectral locus, in relation to the white center, by defining different distance of each spectral color that must represent, with every length, the amount of color necessary for 2 complementary colors to result white when mixing. It may be necessary to use the same amount of blue and orange to achieve white, but the amount of violet will be much higher than the amount of yellow to achieve the same white. In this way, the distances of each wavelength vary, generating a distortion in the spectral locus that results in an irregular arc. The CIA generates a colorimetric diagram in 1931, giving greater importance the position of a coordinate that must represent all the wavelengths mixed at the same intensity, which results in a spectral locus in the form of a horseshoe very projected towards the green, losing perceptual uniformity in its XY axis. In 1976, the CIA launched new UV dimensions, with the aim to improve Munsell's color patches equidistances, although exaggerating this time the projection size to the spectral violet. Filmlight proposed new uniform projections for spectral locus. The RG plot, in which device triangles have a very symmetric orientation in the vertical axis, and the AB plot based on the opponent process. Unlike a proposed LAB space to represent with the L lightness dimension, Filmlight proposed an EIB space with the aim of representing color that exceeds the lightness range, replacing the L dimension with the E from exposure, designing to include the representation of fluorescent or emissive object within the diagram. Color distortion curves edit a color space in a non-monotonic way by using as dimensions some non-perceptual color attributes, such as the HSL color model. Other tools allow color distortions for interfaces that work on control points, similar to curves but developed on the chromacity plane, allowing bidimensional non-monotonic distortions that also usually brings undesirable effects on the image. Based on the colorimetric EAB plot, Filmlight develops a revolutionary tool called X-grade, allowing color distortion for monotonic functions controlled by 3 vectors. Evans introduces a visual attribute called brilliance in color glossaries to refer to surfaces that seem to emit color by themselves, which deserves a particular study in colorimetry. In general, saturation controls do not modify at all the intensity of achromatic colors, but modify the intensity of the colors that have some chromaticity, and by increasing saturation, now they seem to emit light, or said in terms of Evans, increasing brilliance. In order to reduce these effects, Filmlight develops tools capable of mitigating it. Even on devices with emissive screens, any observer can recognize the portrait of objects that originally in their capture were reflective and differentiate them from the fluorescent or emissives. Thanks to the mechanism of light adaptation that causes the white object with diffuse reflectance. In SDR and HDR devices, try to maintain a continuous light intensity for this type of object, such as streak, so that the viewer adapts to this value and recognizes greater intensity values as brights. With a well-designed perceptual model, this parameter appears as the option to provide natural colors during its edition. The cerebral cortex has parts dedicated to higher stages of the visual process. Machine learning tries to emulate these processes capable of recognizing patterns that are repeated between different images. The algorithm training process is aimed at recognition of different visual characteristics, such as the segmentation of the image in its parts, the depth estimation, the orientation of the surface normals, or even facial recognition and their three-dimensional tracking. These tools are applied to alter not only the color schemes of an image, but also the composition of the color of the image, being able to modify the accent and the dominant with the use of different tools based on machine learning. The images are captured with a palette given by the art and photography directors. But thanks to the depth map, combined with the depth keyer, it is possible to alter the background and the foreground independently, being able to make an image of analogous color and enhancement of the figure through complementary balances by generating a chromatic contrast and color separation, modifying the sensation of depth with the aim of changing the expressiveness of the scene. In addition to the set of visual characteristics that make color, there are other sets that make the space domain of the image, where it's not the shapes that should be recognized, but the spatial frequencies. The visual system has different areas dedicated to the recognition of plane and details. Low and high spatial frequencies can be editable in separated contrast controlled, such as the texture equalizer, the texture smoothing, and the boost of contrast, detail, range, and shadows, which function as an interaction between contrast and space domains, called crosstalks. Crosstalk happens when sensory signals of different sources. These interferences are emulated in Baselight from the simple mixture between RGB channels, between opponent YB and opponent RG, or through modification according to the spatial frequency and their blending controls, combining many perceptual stages at the same time. In optics, crosstalks happen between intensity and spatial domain, such as the point spread function, where a point of high light intensity spreads in the retina, or within an optical system or an electronic sensor. By increasing the bright intensity of an image, Baselight allows to emulate this spread with its texture highlight tool, resulting in a more natural and less artificially crisp contrast. Baselight has emulators who act in the spatial domain, allowing to add in the image characteristics of optical systems such as chromatic aberration, the form of the diaphragm during the addition of the field depth with the bokeh tool, increasing the shutter time, add characteristics of the film support such as grain and the halation effect, or try to reduce the distortion of the lens, flickering light sources, noise and grain reduction with no needs of plugins. The Baselight color administration allows different workflows within his same system framework, such as ACES 1.3 and 2.0, or the use of proprietary workflows such as ARRI and Red camera manufacturers, in addition to the proprietary Filmlight workflow TrueLight, the GCAM. The color appearance model, or CAM, is the key part of modern colorimetry, where the colors are not evaluated only because of its similarity of stimuli with 3 spectral colors, but also the effects of changes in the appearance of the color that arise when varying of absolute light intensity and the influence of the viewing environment around the screen. The contrast relationship is the result of dividing the absolute intensity of the brightness peak present in an image by its darkest part. But even maintaining this constant relationship, images that reproduce its minimum and maximum with greater absolute intensities seems to have more contrast and color. When moving the same image between different screens, for example from the 48 nits theater screen to a 200 nits TV screen, although both screens have the same contrast ratio, the image will be more contrasted and colorful on the TV. The same will happen again when passing to a 1000 nits HDR screen, by keeping the contrast ratio, and with the opposite effect when you return to the theater screen. The surround intensity also collaborates with the change of appearance, as a dark tone looks darker when it is surrounded by a brilliant surround. Other more complex and less sensitive effects also happen within a color administration that does not try to compensate for this perceptual phenomena, which are estimated at TCAM with the aim of facilitating and accelerating the process of final deliveries from different screens, focusing the colorist time in the artistic process by reducing the trim pass tasks. Now, I recommend you to download a Baselight trial version and take an experience with every tool to feel these comparative advantages for yourself. First, make a balance with the base grade operator, which although other developers try to imitate its functionality, this tool acts in a much more predictable and pleasant way for the image. The look presets in Baselight are made of the powerful Chromatic tool, which are not based on non-editable 3D LUTs that work in a particular color space or color administration. Being able to modify these initial looks to taste and combining them with each other without possibility of damaging the image. You can add the Chromatic stages that you want, delete them, rename them, and visualize the perceptual space in RGB cube, EAB, or as radial EAB. Experiment with the contrast boost stages and highlight bleach to desaturate the light sources, or with neutral tint add color to the chromatic axis. In addition, operators can work within a perceptual space by sectors, such as brightness sector, saturation, and the skew and squash. You will see that in Baselight, you will not need any plugin to make your look development. It also adds an X-grade operator and freely modifies color coordinates, even selecting them directly to the image. In the advanced versions, you can combine color operator with depth maps and experience the complete potential of the application. Thanks for watching.